The Western Front in 1915 was not merely a protracted line of trenches, it was a devastating proving ground where 19th century military doctrine collided violently with 20th century industrial capacity. For Britain, the sheer scale of mobilization was an avalanche that buried all peacetime planning and assumption. By the spring of that year, the British presence, the British Expeditionary Force, BEF, had swelled to nearly 1.5 million men deployed across France and Belgium. This was a force of a magnitude that the Duke of Wellington, who commanded perhaps 70,000 men at Waterloo, could not have conceptually grasped. The operational challenge was not fighting, it was simply sustaining existence. Every single one of these million-plus men required far more than just ammunition and rations. They needed somewhere to sleep, a place to eat, a dry spot to store their valuable equipment, and crucially, a secure refuge from the relentless, indiscriminate brutality of modern shellfire. The traditional military answer, refined over centuries of colonial and continental campaigning, was woefully simple and immediately irrelevant. Commandeer existing buildings, hastily throw up makeshift wooden barracks, and requisition local farmhouses. These were the established methods, tested in smaller, more geographically contained conflicts. However, on the Western Front, these solutions were disintegrating. Faster than military planners could possibly replace them, turning the logistical backbone of the BEF into a state of constant, desperate triage. The rise of indiscriminate destruction. The primary catalyst for this infrastructural collapse was the terrifying evolution of German artillery. No longer was artillery reserved for careful, measured attacks on fortified positions. It was now a tool of mass destruction and area denial. The transition from shrapnel to high-explosive, HE shells, particularly the larger calibers, meant that structural integrity was an obsolete concept. A single 150mm 5.9-inch HE shell, or the infamous Jack Johnson, 11-inch howitzer round could reduce a solid, centuries-old stone farmhouse, built to withstand generations of storms, to an instant chaotic pile of rubble. The concussion alone was enough to tear the structure apart. Even without a direct hit, wooden barracks, the standard quick-build solution, fared even worse. They did not simply collapse. They would splinter into lethal matchsticks, sending jagged, deadly fragments of wood hurtling in every direction, often injuring or killing men who had survived the initial explosion. These secondary injuries, caused by debris from the very structures meant to protect them, became a horrifying feature of the daily casualty lists. The British Army watched helplessly, logging the losses each morning. Another dozen buildings gone. Another few hundred men left exposed to the elements, their brief period of rest annihilated. The destruction wasn't limited to the front-line trenches. The true crisis of accommodation occurred behind the trenches, the logistical zones and the volunteer flood. Behind the shallow, exposed front lines lay the vital logistics zones. These sprawling areas housed supply depots, field hospitals, ammunition dumps, transit camps, and rest billets. They were the engine of the BF. Where supplies were stored, injured men were treated, and exhausted troops rotated through for their mandatory, if often brief, period of rest. Here, conventional buildings were proving catastrophically inadequate for reasons of both volume and vulnerability. Britain's military machine had expanded with terrifying speed, far faster than anyone in the War Office had anticipated. Following Secretary of State for Warlord Kitchener's famous call to arms in the summer of 1914, "Your country needs you," volunteers flooded recruitment centers. This unprecedented influx of manpower, primarily driven by patriotic enthusiasm rather than conscription, which would not be introduced until 1916, swelled the BF to numbers that would have been mathematically absurd just 12 months prior. By late 1915, this massive army, Kitchener's new armies, needed shelter, and they needed it across hundreds of square miles of occupied French and Belgian countryside. The required shelter had to meet an impossible set of demands. Speed. They needed it erected in days, not weeks. Cost. It had to be cheap enough to build by the tens of thousands. Survivability. It had to withstand the reality of modern shell-based warfare, the failure of traditional methods. The traditional construction industry simply could not meet these demands, primarily due to resource and skill limitations. Brick and mortar, A proper, durable brick building required skilled masons and weeks of intensive labor. These skilled tradesmen were desperately needed for other critical work, repairing railway lines, building port facilities, or simply maintaining the industrial capacity back in Britain. Furthermore, the materials, bricks, stone, lime, and cement, were all needed elsewhere, placing an intolerable strain on shipping and domestic production. Timber structures, huts, wooden structures, though faster to erect, required an enormous, unsustainable quantity of timber. Wood was the single most critical building material of the entire war effort. It was required for trench supports. Millions of feet of timber were needed to shore up the collapsing sides of the front-line trenches, preventing soldiers from being buried alive in the relentless mud. Ammunition crates. Every single artillery shell and rifle bullet required a wooden crate or box for transport and storage. Railway sleepers, bridges and tool handles. 1,000 other military necessities consumed the remaining timber stocks. The competition for lumber was fierce, making large-scale wooden barrack construction logistically untenable and strategically unwise. The scourge of weather and disease. Adding to the destruction caused by enemy action was the relentless, silent enemy, the weather. The winter of 1914 to 1915 was remembered as particularly brutal, a continuous cycle of freezing cold, heavy rain, and the ubiquitous, inescapable French mud. The troops, many housed in makeshift canvas tents, the standard issue of a bygone era, discovered that these shelters offered virtually no protection. They were designed for summer camps and quick maneuvers, not prolonged exposure to a continental winter. The medical consequences were horrifying. Respiratory diseases tore through the overcrowded, damp, and drafty camps. Men who had bravely faced German bullets and survived the initial shock of trench warfare succumbed to pneumonia, bronchitis, and influenza in inadequate shelters. The medical officer's reports, arriving daily at the War Office, made for grim, damning reading. In many periods, the Army was losing more men to exposure, frostbite, and illness than some divisions were losing to direct enemy action. This was a catastrophic drain on manpower, morale, and fighting capacity. An army that could not rest, dry out, or recover was an army that would eventually break. The impossible equation for the War Office. The planners at the War Office in Whitehall found themselves wrestling with an equation that seemed to defy solution. They needed a solution that was simple to erect, buildability by unskilled soldiers, infantrymen, drivers, and clerks, not professional carpenters. Durable, resilient, must withstand the concussion and shrapnel of shellfire better than existing structures. Easily transported, must be shippable to France through a network already struggling under the weight of primary supplies. Mass-producible, affordable enough to build on an unprecedented scale. The list of fatal flaws. Every existing or proposed solution examined by the military engineers and architects in 1915-1916 had a distinct fatal flaw that rendered it unviable for mass deployment. Concrete bunkers, pillboxes. Too slow to construct, requiring specialized materials and curing time. Too expensive for non-critical troop rest areas. Only viable for permanent, high-value defensive positions. Reinforced brick buildings. Required too many scarce. Skilled masons and weeks of labor. Logistically impossible to sustain the material supply across the channel. Expanded metal or corrugated iron shacks. Flat roofs. While using readily available metal, they proved too fragile. The flat or shallow-pitched roofs buckled and failed instantly, under the suction and compression forces of a nearby blast wave. They offered little more protection than wood against collapse. Wooden huts, Nissen-type predecessors. They required too much wood, were slow to mass produce, and were highly susceptible to incendiary shells. A single phosphorus round could set an entire barrack alight, turning it into a deadly furnace. Canvas tents, rotted quickly in the relentless damp, offered zero protection against cold, and were utterly useless against even small shrapnel. What Britain's military required was not an improvement on an existing design, but a radical invention. They needed a shelter that could combine the durability and fire resistance of steel with the speed and efficiency of prefabrication. They needed to achieve geometric strength without relying on heavy, slow materials. They needed a design that fundamentally understood and worked with the physics of explosion, a problem of perspective. The military establishment, dominated by traditional architects and career, royal engineers trained in masonry and fortification, looked at the problem through the lens of traditional building. Walls, roofs, foundations. They sought a stronger wall or a faster roof truss. They focused on linear strength. The solution, however, lay in a completely different domain, structural loads and geometry. The person who would finally unlock this puzzle was someone entirely outside the architectural mainstream. They needed someone to think differently about the fundamental problem of protection through shape. They just didn't know that the answer was about to arrive from a mining engineer, a man whose entire career had been spent deep underground, battling the silent, crushing pressures of rock and earth. Lieutenant Colonel Peter Norman Nissen was not supposed to revolutionize military architecture, but his unique perspective, developed far from the conventional battlefields and building sites, would prove to be the most vital. Technical insight of the Great Wars. Logistics battle. The unlikely architect, Peter Norman Nissen. The military crisis detailed in Part 1. The unholy trinity of explosive destruction, logistical starvation, and material scarcity demanded a solution that simply could not originate from conventional thinking. The problem was too profound, too fundamentally opposed to the principles of brick, wood, and mortar. The man who provided the answer, Lieutenant Colonel Peter Norman Nissen, was the most unlikely of saviors for the architecture of war. Born in America to Norwegian parents and raised in the rugged, resource-driven landscapes of Canada, Nissen's entire professional life had been spent, not in the academic halls of architectural schools or on parade grounds, but deep underground. His career had been built on the grim, challenging work of mining engineering. For decades, he had navigated mines and quarries across North America, from the gold fields of the Yukon to the copper mines of Arizona, learning one immutable truth: how earth and rock behaved under pressure. His expertise lay in understanding structural loads, material properties, and, most critically, the behavior of curved surfaces when subjected to immense, continuous external stress, the constant, crushing weight of geological strata. When the Great War erupted in 1914, Nissen, then a civilian engineer, was gripped by the same patriotic fervor that swept across the empire. He volunteered for service and the British Army, desperate for men possessing deep, technical skills that could be rapidly applied to the complexities of modern conflict, commissioned him as a lieutenant in the Royal Engineers. By early 1916, Nissen's unique background had brought him into the very eye of the logistical storm, stationed near the ravaged city of Ypres in the heart of the Western Front. The engineer at Ypres, a crisis seen anew. Ypres was a study in destruction, a perpetual graveyard of stone, wood, and metal. Unlike the career military, engineers and architects around him, men who saw the crisis through the lens of failed conventional construction, Nissen approached the accommodation problem with the cold, pragmatic perspective of a man who solved life-and-death structural failures daily. He didn't see broken barracks. He saw failed load distribution. He didn't see piles of rubble. He saw materials that had surrendered to concentrated perpendicular force. His mind, trained by years of battling cave-ins and stress fractures deep beneath the earth, instinctively analyzed the external pressures, shell blast, shrapnel impact, wind, and rain, as if they were geological forces. For Nissen, a bursting shell was simply a momentary but intense stress fracture in the air and ground, and the problem was to design a structure that would deflect and distribute that force, not resist it head-on. His experience in mines had taught him that in a subterranean environment, a square-cut passage was inherently weak. The ceiling and corners provided perfect stress risers, points where external pressure would concentrate, leading inevitably to collapse. The strongest, most stable, and most enduring structure in mining was the arch or the continuous curve, the natural shape of a tunnel. The arch successfully transformed vertical and lateral pressure into a continuous, distributed stress path that led down and out into the bedrock, preventing any single point from bearing a catastrophic load. This principle, common in civil engineering for bridges and viaducts, had been entirely forgotten when dealing with fast, temporary military shelters. Nissen merely needed to lift the principle of the mine tunnel out of the earth and plant it on the surface. The breakthrough moment. The resilience of scrap metal. The crucial intuitive leap occurred during a routine inspection of damaged supply depots in the Ypres salient. The scene was depressingly familiar. Shattered remnants of brick and splintered timbers everywhere. But Nissen, a keen observer of material failure, noticed a striking anomaly. The corrugated metal, roofing sheets, often just cheap, utilitarian cladding used on temporary sheds, had survived remarkably intact. These sheets, often discarded or blasted off their original structures, lay scattered across the ground. While the flat sections showed creases and shrapnel holes, those pieces that had been bent into an arc or curve, either accidentally by blast force or originally during installation, exhibited a dramatic increase in structural rigidity. They hadn't buckled or folded over like flat sheets of steel. They retained their curved shape, absorbing the shock. Nissen realized that the metal was strong enough, and the curve was the key to unlocking its potential. Others might have seen scrap. Nissen saw a fundamental physics lesson. A curved sheet of corrugated metal could withstand forces that had utterly destroyed heavier, more expensive materials. The implications were instantaneous and revolutionary. Why rely on complex internal frameworks, load-bearing walls, and skilled labor when you could build an entire structure from nothing but curved metal sheets? The design, simplicity as genius. The concept that Nissen sketched during a tea break in March 1916 was one of devastating simplicity, a design so elemental it verged on childish genius. The material used standard, cheap, and mass-produced corrugated iron sheets. This material was already being churned out in vast quantities by British mills for barns, warehouses, and agricultural roofing, immediately solving the resource scarcity issue. The geometry. Curve the sheets into a perfect semicircle, a half arch. This shape would inherently distribute external loads. The assembly. Bolt the semicircular sections together longitudinally, end to end, forming a continuous tube or tunnel. The ends. Fit simple timber end walls, the only component, requiring basic carpentry to close the structure, adding a door and perhaps a small window. The resulting structure would be entirely self-supporting. There would be no internal posts, no load-bearing beams, and no complex roof trusses. The sheer geometric strength of the continuous arch, reinforced by the corrugations, would provide all the strength needed, challenging architectural dogma. Nissen's proposal flew directly in the face of all established architectural dogma. The traditional building world required deep foundations to transfer the load of heavy walls and roofs to the stable subsoil. Vertical load-bearing walls to carry the weight of the roof downwards. Engineered roof trusses to span wide distances and prevent the roof from sagging. A structure that was literally a thin metal arc bolted to the ground was an insult to the profession. Traditionalists would argue that you couldn't simply bend some cheap metal sheets into an arc and call it architecture. It lacked permanence, dignity, and proper structural engineering principles. Yet Nissen, the mining engineer, was not constrained by those principles. He understood that in the high-stress environment of the Western Front, permanence was an illusion, and the strength of a building was not measured by its mass, but by its kinetic reaction to external force. The physics of the arch. Deflection, not resistance. Nissen's insight was purely about physics and pressure dynamics. He knew that the semicircular shape was inherently superior to conventional, rectilinear designs when facing explosive force. An explosion generates a pressure wave, a massive, near-instantaneous fluctuation in air pressure. When this wave strikes a traditional flat wall or a peaked roof, the force hits the surface perpendicularly. All that explosive energy is concentrated directly at the point of contact, creating immense localized shear stress that inevitably leads to structural collapse. The wall fails inward, or the roof is uplifted and torn off. The Nissen Hut's curve solved this elegantly. Glancing blow, a blast wave approaching. The curved wall could only impact it perpendicularly. At one tiny, instantaneous point, everywhere else the curve presented an angled surface. This dynamic transformed the direct, shattering force into a glancing tangential stress. The blast wave slid up and over the arc, effectively dissipating its energy along the surface, rather than attempting to smash through it. It was the architectural equivalent of a bullet ricocheting off a curved, armored surface. Continuous distribution. Because the hut was one continuous arc bolted together, any force hitting one section was instantly distributed across the entire circumference. A push on the side didn't just stress the side wall, it simultaneously pressed down on the top of the arch and pushed outward against the base on the opposite side. The entire structure acted as a cohesive single unit, sharing the shock load and transmitting residual energy down into the ground, like a finely tuned spring. The multiplier effect of corrugations. The key to preventing the thin metal from simply crumpling under this distributed load was the second element of the genius design, the corrugations. A flat sheet of metal is structurally weak. It flexes easily if you apply pressure perpendicular to its surface. But when you introduce the series of ridges and valleys that define corrugated iron, you dramatically increase its rigidity. Each wave in the metal creates what engineers call a moment of inertia, an increased resistance to bending. By bending the sheet, you are no longer trying to bend a flat plane. You are trying to bend dozens of tiny, interlocked right angles simultaneously. The geometry locks together, transforming a flexible sheet into a rigid panel. The corrugations also created crucial multiple load paths. When a force, be it blast, snow, or wind, hit the structure, the energy couldn't travel through one continuous piece of flat metal that could buckle or tear in one spot. Instead, the energy had to navigate through an endless series of peaks and troughs. Each crest and valley acted as a tiny stress break, momentarily redirecting and successfully dissipating a portion of the energy. By the time a powerful explosive force had traveled through several corrugation cycles, it had been tamed, losing much of its destructive potential before reaching the next layer of metal. This marriage of the structural arch for deflection and distribution, and the corrugated profile for rigidity and energy absorption created a shelter that was lightweight, cheap, and fast, yet geometrically superior to structures relying on sheer mass. From sketch to prototype, the desperation for a solution. Nissen took his detailed sketches and his compelling structural theory to his commanding officer in April 1916. He likely expected the stiff skepticism reserved for all radical, untried ideas in a conservative military establishment. Instead, he found an environment of deep, tactical desperation. The situation had worsened. Casualties from exposure and inadequate rest were mounting, and the vast scale of the forthcoming Somme offensive, a battle that would deploy hundreds of thousands of additional troops, required a revolutionary solution to the housing problem immediately. The army couldn't afford weeks of debate. They needed experimental shelters tested yesterday. The need for rapid, survivable accommodation had transcended the need for conventional architectural approval. Within an astonishingly short period of 3 weeks, the first operational Nissen Hut prototype was erected. Near Ypres, it was a semi-cylinder, measuring 16 feet wide and 36 feet long. The true measure of its genius was demonstrated in its construction time. It was assembled by just 3 men using basic tools in less than 6 hours. This alone, a structure of this size erected faster than a single meal could be served to the entire detachment, was a tactical victory. The prototype looked, as many joked, like a massive, corrugated tin can cut lengthwise. It looked flimsy. Officers walking past it in late April 1916 scoffed at the thin metal shell. They questioned if a strong wind would simply pick it up and deposit it in the nearest field. The structure used a fraction of the material of a wooden barrack. The skepticism was palpable, the jokes cruel. The test, however, was about to make the entire BEF stop laughing and start building. The moment of testing in late April 1916 at Ypres was charged with both skepticism and desperate hope. The prototype Nissen Hut stood on the open ground, a lone, corrugated semi-cylinder that looked In the eyes of many seasoned officers, absurdly flimsy. Its thin metal skin and lack of any visible heavy reinforcement seemed to mock the established engineering standards that had failed so spectacularly on the front. Skepticism was the prevailing mood. Some officers reportedly took bets on whether the structure would survive the blast, with many predicting it would be reduced to a twisted heap of scrap metal or simply blown away by the wind from the explosion. The first trial was designed not merely to test durability, but to push the limits of what was considered survivable for a temporary structure. A high-explosive charge, powerful, enough to simulate a close-range artillery hit, was placed just 20 feet from the hut's side. This proximity was deliberate. A similar blast would have annihilated a standard wooden barracks, reducing it to splinters and guaranteeing high casualties among the occupants. The detonation was deafening, sending a massive shockwave rippling across the testing ground, accompanied by a cloud of dirt, smoke, and debris. A collective intake of breath swept through the small group of observers. Royal engineers, staff officers, and Peter Nissen himself. When the smoke cleared, the impossible had happened. The Nissen Hut stood essentially undamaged. The initial inspection revealed that the blast had stripped away some mud and debris around the base, and a few bolts near the impact zone had loosened slightly. But the overall structural integrity was sound. The hut was still a hut. The jokes about the oversized tin can immediately ceased, replaced by stunned silence and a flurry of technical questions. They had witnessed not a miracle, but a perfect demonstration of fundamental physics that contradicted the very essence of traditional military construction. The dynamics of blast deflection. The secret to the hut's survival lay not in its material strength, but in its geometry, specifically how the continuous curve interacted with the intense, near-instantaneous pressure wave of the explosion. When an explosion occurs, it generates a supersonic wave of compressed air, followed by a momentary vacuum, suction. When this blast wave strikes a flat or linear surface, like a conventional wall, it delivers its energy perpendicularly, a direct head-on impact. This concentrated force, known as the incident pressure, is what shatters walls and tears roofs apart. The Nissen Hut, however, offered a constantly changing, angled surface. The blast wave, approaching the arc, could only hit the metal perpendicularly at a single, infinitesimally small point directly facing the blast center. Everywhere else, the curve presented a highly angled surface. This angle transformed the destructive force into a tangential stress that ran along the circumference of the hut. Instead of being stopped and absorbed, the energy was smoothly deflected. It slid up and over the arc, effectively dissipating the pressure wave into the air and harmlessly around the structure. This deflection was crucial because it reduced the most dangerous element of the explosion, the peak incident pressure. The curve essentially minimized the surface area that could be hit head-on, drastically lowering the stress on the metal. Load sharing and structural integration. The continuous curve did something even more sophisticated than simple deflection. It achieved a principle known as load sharing. In a traditional building, a wall is an independent unit. Damage to that wall often leads to its isolated failure and the subsequent collapse of the roof. The Nissen Hut, being a single integrated arc, acted as a cohesive unit. Any force striking one point was immediately distributed around the entire structure. An impact on the side transmitted force up to the crown top of the arch. The pressure at the crown was then channeled downwards and outwards to the base of the opposite side. The structure behaved like a unified spring, flexing minimally to absorb the shock and transferring the residual energy into the ground. This meant that the failure of one small section did not lead to the catastrophic failure of the whole structure. If a single panel was severely damaged, the panels next to it, still supported by the continuous arc, maintained their shape and structural integrity, preventing the cascading collapse typical of conventional construction. The role of corrugation in energy absorption. The corrugated profile was the necessary complement to the arch's geometry. While the curve handled the macro dynamics of deflection and distribution, the corrugations managed the microdynamics of energy absorption and rigidity, increased rigidity. The ridges and valleys locked the thin sheet metal into a surprisingly rigid form. Applying force to a flat sheet makes it bend easily. Applying force to a corrugated sheet forces one to bend dozens of tiny, interlocked right angles simultaneously, dramatically increasing the material's moment of inertia, resistance to bending or buckling. Internal load paths. Each corrugation acted as a small, separate structural member. When the blast wave, having been deflected by the arc, still managed to impact the metal, the force had to navigate an endless series of peaks and troughs. The energy didn't travel along a smooth path. It was forced into a complex, tortuous route. Each peak and trough absorbed a minute portion of the energy, dissipating the destructive power before it could concentrate enough to tear the metal. Engineers later concluded that the design was successful because it was simultaneously flexible and rigid. It was flexible enough to absorb the sudden impact and expansion of a blast wave without shattering like brick or stone, yet rigid enough to hold its geometric shape under sustained pressure. The shell fuse factor. Sophistication against itself. The successful initial test led to further, more realistic battlefield trials that revealed an unexpected layer of survival. The Hut's thin metal skin was often too weak to activate the enemy's artillery fuses reliably. Modern HE shells were designed with fuses that required a specific, sharp deceleration, an impact profile typical of hitting stone, thick wood, or earth to arm and detonate upon impact, a common delayed action fuse setting. When a shell struck the Nissen Hut's thin, curved steel, two things often happened: glancing and missed impact. Due to the angle of the curve, the shell often glanced off the surface. Insufficient resistance. The thin metal provided insufficient resistance to generate the sharp deceleration needed to reliably trigger the fuse mechanism. The shell, designed to penetrate heavy materials before exploding, would either glance off and detonate, harmlessly 20 or 30 yards away in the open field, or fail to detonate at all, having not registered the expected impact profile. The British Army was, in effect, using the shell's own sophistication against them. Immediate deployment, the Somme Offensive, 1916. The definitive validation of Nissen's design came not in a controlled test, but during the brutal reality of the Somme Offensive, which began in July 1916. The massive scale of the operation required logistics and support for hundreds of thousands of additional troops, instantly amplifying the accommodation crisis. The Army could no longer wait for perfect solutions. They needed any working solution, and the Nissen Hut was the only one that met the criteria of speed, transportability, and survivability. The experimental phase was rapidly bypassed. Hundreds, then thousands, of Nissen Huts were immediately ordered and began moving to France. They were erected across the logistic zones behind the lines, serving as medical clearing stations, quickly established hospitals near the front, supply depots, critical storage for ammunition and rations, reserve troop quarters, dry, relatively safe rest areas for men rotating out of the trenches, communication centers, command posts for transmitting orders. They were no longer curiosities, they were battlefield necessities. Survival under fire, field reports. Reports filtering back from the Somme sector provided irrefutable proof of the Hut's capabilities. These were not controlled tests. They were incidents of random, sustained exposure to real German bombardment. Near Albert, a supply depot housed in a Nissen Hut took a close range, hit from a powerful 5.9-inch shell. The round, designed to punch through heavy concrete, struck the curved roof at an acute angle. Instead of penetrating and detonating inside, the shell glanced off the corrugated curve, skipping across the ground to explode harmlessly dozens of yards away. The clerks inside, who had dropped to the floor, stood up moments later, suffering nothing worse than temporary deafness. The hut had a significant dent, but the structural integrity was maintained. Near Pozières, a field medical station survived 3 separate near misses that left massive craters deep, enough to swallow an artillery gun. The conventional structures nearby were pulverized, but the Nissen Hut, though severely shaken and peppered with shrapnel, remained functional, allowing the medical staff to continue treating the wounded. At Beaumont-Hamel, troops sheltering in a Nissen quarters during a protracted bombardment described the experience as terrifying. The noise was like being inside a drum beaten with hammers. Yet the continuous unified shell refused to collapse inward. The men were safe, protected by a continuous arc that simply wouldn't yield its shape. The absence of secondary destruction. The key difference observed in the field was the absence of secondary destruction. When a shell hit a brick or wood building, the initial blast caused the walls to collapse inward, turning the structure itself into a second wave of deadly projectiles, shattering stone, splintering wood. The Nissen Hut's shell, being continuous, had nowhere to collapse to. Blast a hole in one section, and the surrounding corrugated metal structure, still part of the stable arc, remained geometrically sound. The failure of one part did not compound the damage exponentially. This structural resilience translated directly into significantly lower casualty rates. In comparative shelling zones, while wooden barracks suffered upwards of 70% casualties among occupants, the Nissen Huts reported rates as low as 12–15%, often from shrapnel that penetrated the thin sides, but rarely from structural collapse itself. By the autumn of 1916, the data was conclusive and the debate was over. The War Office stopped viewing the Nissen Hut as an experiment. They began ordering the curved shelters in vast quantities, recognizing that this simple, reproducible design was the only viable, scalable solution to the critical accommodation crisis on the Western Front. The mining engineer's concept had been tested by fire and validated by battlefield necessity, following the unequivocal validation during the bloody battles of the Somme. The Nissen Hut transitioned instantly from an experimental curiosity to a military imperative. The reports were clear. It was the only accommodation solution that was fast, affordable, and critically, survivable under modern artillery fire. The tactical and strategic implications were immense. A commander no longer had to rely on vulnerable, slow-to-repair stone buildings or highly flammable wooden barracks. They could establish secure rest and logistics points almost overnight. By the autumn of 1916, the British War Office stopped counting in dozens and began ordering in the thousands. The challenge now shifted from design to delivery. How could Britain's already overburdened industrial infrastructure suddenly churn out tens of thousands of these unique shelters monthly without diverting crucial resources from primary ammunition and weapon production? The answer lay in the sheer, elegant practicality of Peter Nissen's design, a practicality born not of architectural ambition, but of a miner's instinct for resource efficiency. The design required no specialized manufacturing whatsoever. Every single component could be produced using existing equipment and readily available materials, already in production across Britain. Manufacturing and material scarcity solved. The core of the Nissen Hut was corrugated iron sheeting. This material was already being produced in staggering volumes for non-military uses. Agricultural roofing for farm buildings, cladding for vast industrial warehouses, and temporary enclosures. The factories that had been producing these civilian goods, primarily steel mills in regions like Sheffield and Birmingham, simply had to adjust their rolling mill specifications. Instead of producing flat or shallow-pitched sheets, they adjusted their output to produce panels curved, precisely to Nissen's specifications, the perfect semicircular arc required for structural integrity. The shift was one of measurement, not machinery. The factories didn't need to retool their entire operation. They just needed new dimensions. This eliminated the major logistical bottleneck that plagued other wartime projects, which often required building entirely new, specialized production facilities. Steel mills rolled the flat sheets and then cold rolled them into the specified arc. Quality control was simple. Did the panel match the template curve? Timber yards, Scotland and the North, cut the simple flat-end walls. These required minimal carpentry. Skill, just the ability to cut a semicircular profile into standard planks and install the necessary door and window openings. Hardware producers, the Midlands. The connectors required nothing exotic. Standardized bolts, nuts, and simple fasteners were mass-produced by the ton, leveraging existing capacity in the massive Midlands manufacturing base. This modular, low-tech, and scalable production method meant that by spring 1917, British factories were manufacturing the components for over 10,000 Nissen Huts per month, and the rate was constantly accelerating. The logistics of the kit, The genius of mass production extended directly into logistics. The Nissen Hut was not shipped as a finished, bulky structure. It was shipped as a complete compressed kit, the original flat-pack shelter. Every single component needed for one shelter was bundled together. The curved steel panels, the timber end walls, the doors, the window frames, often simple glassless openings or shutters, and the heavy bags of bolts and fasteners. These kits were designed with transport efficiency as the highest priority. Compactness. The curved metal sheets could be nested inside one another, dramatically reducing the volume required for shipping. Weight. The total weight of one standard hut kit was carefully managed. No single component was so heavy or cumbersome that 4 men could not easily lift it. This ensured that handling could be done entirely by manpower at ports and railheads, without relying on scarce cranes or mechanized lifting equipment. Road transport. The standard model, 16 feet wide by 36 feet long, was designed so that 2 complete hut kits could be loaded onto a standard British Army lorry. This meant that a small convoy could rapidly transport enough shelter for a substantial number of troops. The design transformed the ability to project shelter forward, right up to the newly captured ground. All these components converged at massive assembly and staging points near British ports. They were checked, crated, and loaded onto the ships crossing the English Channel, where the shipping network was already straining under the demands for shells and rations. The fact that the hut components took up less vital cargo space than the equivalent volume of brick or lumber was a strategic victory in itself. The Nissen Hut was, in effect, consuming the least strategic resources to provide the most strategically vital necessity, shelter. The 4-hour assembly revolution. The most dramatic illustration of the design's genius came at the point of use the assembly process on the French and Belgian soil. The army was not allowed to pull skilled carpenters or masons from the war effort. The huts had to be erected by the soldiers themselves, infantrymen, drivers, clerks, or engineers with minimal construction expertise. Nissen's design was effectively construction by numbers, requiring only basic strength and the ability to operate a spanner, wrench. The simplified assembly sequence was as follows. Foundation. Soldiers cleared a level area and laid a simple timber foundation beams directly on the ground. No deep digging or complex foundations were required, as the structure's load was distributed horizontally across the entire length. The arc. Crews positioned the pre-curved metal sections vertically. Starting from one end, each panel had pre-drilled holes that perfectly aligned with its neighbor. Bolts were passed through and tightened. The tunnel. Work progressed rapidly, down the length of the base until the curved sections formed a complete, continuous tunnel. End walls. The pre-cut timber end walls, which perfectly matched the semicircular metal profile, were simply nailed or bolted into place, using the corrugations as natural attachment points. Waterproofing. Basic waterproofing, usually in the form of tarred felt strips, was placed over the longitudinal bolt seams, protecting the interior from the ever-present rain. The result was astonishing. The entire process, from unpacking the kit to having a weather-tight shelter, took a team of 4 men approximately 4 hours for the standard model. Strategic and tactical flexibility. This phenomenal speed had immediate and profound strategic and tactical implications that commanders instantly grasped. Mobility. An infantry division relocating to a new sector could dismantle their old huts, load the kits onto lorries, move 50 miles, and have their accommodation re-erected before nightfall. Shelter was no longer a static, limiting factor in operational movement. Rapid infrastructure. A new field hospital, a casualty clearing station, or CCS, could be made operational within hours of the site being secured. Ammunition dumps and fuel. Storage depots could be expanded overnight to meet increased logistics demands during an offensive. Manpower efficiency. By reducing the construction time from weeks for brick or days for wood to mere hours, the Army released valuable, capable soldiers from construction duties, freeing them to return to the front line or perform specialized tasks. By the end of 1917, the Nissen Hut had cemented its place as the unseen weapon of the BF. Its structural genius and industrial simplicity had solved the logistics bottleneck, that could have crippled the war effort. It provided dry, survivable, and rapidly deployable shelter on a scale no one thought possible, supporting the hundreds of thousands of men pushing the line forward. The sheer relentless output, tens of thousands of these curved shelters, demonstrated how Nissen's unconventional approach had won the battle for accommodation, the peace that should have ended the hut. The First World War concluded dramatically in November 1918, the global machinery of industrialized conflict ground to a halt. As the world returned to peacetime footing, military planners assumed that the Nissen Hut, like so many other wartime expedients, from improvised trench mortars to early gas masks, would rapidly fade into obsolescence. It was, after all, a creation born purely of desperate necessity, not of permanent architectural ambition. The initial intention was for the huts to be a temporary, disposable solution to a catastrophic accommodation crisis. The huts did not disappear. In fact, peace created an immense, unexpected surplus problem and a new set of peacetime necessities that the Nissen Hut was uniquely suited to solve. By 1918, British forces had erected or were in possession of roughly 100,000 Nissen huts scattered across the UK, France, and Belgium, and thousands more in various states of production. The cost of dismantling and scrapping these structures, especially those overseas, was prohibitively high. Furthermore, Britain itself faced an immediate and acute post-war housing crisis. Thousands of returning soldiers needed immediate shelter, and vast quantities of war materials needed dry, secure storage before being sold or repurposed. Civilian adoption and transformation. The Nissen Hut was swiftly adopted for a wide range of civilian and military transitional uses throughout the 1920s and 1930s. Emergency housing. Thousands of huts were brought back to Britain and used as temporary homes for returning servicemen and their families. While often cramped and difficult to heat, they provided quick, dry shelter where none existed, transforming old military camps into temporary, curved-roof housing estates, known colloquially as Nissenville, communities' agricultural storage. The hut's original inspiration, corrugated agricultural sheds, came full circle. They became highly valued on farms across the UK for storing grain, machinery, and livestock, prized for their low-cost, durability, and resilience to harsh weather. Industrial workshops and garages. Factories and small businesses utilized the huts as cheap, quick-to-erect workshops, storage annexes, and vehicle garages. Their wide, pillar-free interior space was ideal for machinery and vehicle movement. Military storage and training. Even the armed forces found they couldn't discard them. Permanent military bases used Nissen huts for storing equipment, as mess halls and as rudimentary training barracks, recognizing that their unique geometry made them excellent against accidental explosion or fire. Compared to conventional wooden stores, the hut endured for 2 decades, not because it was beautiful or comfortable, but because it was perfectly functional, infinitely adaptable, and readily available. It had proven its structural integrity in war, and it now proved its economic utility in peace. The looming crisis. World War II. As the geopolitical landscape darkened in the late 1930s, and the prospect of a second, even larger global conflict loomed, military planners in 1939 rediscovered the Nissen Hut. They faced the same old, impossible equation, only worse. The scale of military expansion was even more rapid than in 1914. This time, however, the threat was not limited to the front lines. It was coming from the sky, directly targeting the civilian and industrial heartlands of Britain. The vulnerability of traditional infrastructure was about to be proven again, but this time against a new and far more destructive force, aerial bombardment. The Nissen Hut, having successfully survived the horizontal pressure wave of artillery shellfire, was now summoned to face the vertical destruction of aerial bombs and incendiaries, the Blitz, a new testing ground. The Blitz began in earnest in September 1940, focusing its devastating power on London, particularly the industrial docklands, and major cities like Coventry, Birmingham, and Liverpool. German bombers dropped high-explosive HE bombs, often weighing 500 pounds or more, along with vast quantities of terrifying incendiary bombs. in concentrations that made even the intense Great War artillery barrages look modest. Nissen huts had been widely deployed across these urban areas, not just on military bases, but repurposed as civil defense posts, command centers for air raid wardens, emergency accommodation, quick shelter for families whose homes had been bombed out, first aid stations, rudimentary medical posts established closer to heavy target zones, industrial storage, housing essential supplies and machinery in factory annexes. The city centers became a new, terrifying testing ground for the hut's resilience. The results were immediate and validated. Nissen's original principles on a grand scale. The dynamics of survival against aerial bombs. The hut's structural geometry proved equally, if not more, effective against the forces generated by aerial bombs. Blast wave deflection, vertical and lateral. An aerial bomb detonates, either on the ground, contact, fuse, or after penetrating, a short distance, delayed fuse. The resulting spherical blast wave hits the hut from above, the side, and below, ground shock. The continuous curved profile successfully deflected all these vectors. The pressure wave was forced to travel around the curve rather than hitting a flat, perpendicular surface, which minimized the concentrated force transmitted into the structure. Ground shock resilience. The low profile and the arc's structural transfer of force directly into the ground made it remarkably resilient to ground. Shock, the seismic wave, generated by a nearby explosion. Traditional brick houses with high, flat walls and rigid corners would often be shaken apart by this ground-transmitted force. The Nissen Hut absorbed it with minimal structural disruption. Shrapnel and debris. While shrapnel from bomb casings and debris from nearby shattered, conventional buildings could perforate the hut's thin metal. Skin in numerous places, the fundamental, load-bearing arch remained intact. The hut could be severely cosmetically damaged, but still functionally capable of sheltering occupants. Fire resistance. Compared to wooden barracks, the steel construction provided crucial fire resistance. Incendiary bombs would burn through the timber and walls if they struck there, but the main corrugated steel body would not ignite, preventing the entire structure from being consumed in a deadly fire. The Silvertown anecdote, a true test. A particularly telling incident occurred in the heavily bombed Silvertown industrial area of London during October 1940. A 500-pound bomb landed directly between two structures, a rigid, multi-story brick warehouse and a low-lying Nissen Hut used as a civil defense depot. The brick warehouse, equidistant from the impact point, was reduced to a dusty pile of rubble. Its rigid structure fractured instantly under the concentrated force. The Nissen Hut suffered extensive secondary damage. Windows blew out. Doors were torn violently from their hinges, and the metal skin was covered in dents and small holes from flying debris. But the structure itself remained upright, geometrically sound and functional. Within 48 hours, workers patched the holes, rehung new doors, and the depot resumed operations. This rapid repairability was another key advantage. Replacing a section of corrugated sheet was fast. Rebuilding a collapsed brick wall took weeks. Global deployment and standardization. The Nissen Hut's performance in the Blitz confirmed its status as a vital part of the military infrastructure. The design was adopted and modified by the Allies. RAF airfields, the Royal Air Force RAF, used Nissen Huts extensively at airfields from Cornwall to Scotland, often the primary targets of Luftwaffe raids. They housed maintenance workshops, where their wide, pillar-free space was essential for working on aircraft parts, sleeping quarters for bomber crews and stores. German intelligence. Photographs taken in 1941 often showed cratered airfields with demolished hangars, but rows of Nissen Huts stubbornly standing. Amongst the wreckage, Royal Navy bases. Huts were used in coastal dockyards like Portsmouth and Plymouth, surviving both German bombing and the brutal, corrosive maritime weather. The curved steel proved resistant to explosive force, though constant maintenance against rust was required in the salt air environment. By the height of WP, the Nissen Hut had undergone a small degree of standardization and refinement, though the core principles remained unchanged. Variations in size, insulation, lining the interior with plasterboard or fiberboard for improved heat retention. and end wall construction were introduced, but the basic 16-foot wide, semi-cylindrical, corrugated steel shell remained the foundation. As Allied focus shifted from defense to offense, preparing for the invasion of Europe, the Nissen Hut stood ready once again for the front line, having proved its worth against a newer, greater force of destruction.